Hello everyone, my name's Craig Roach. I'm a solution architect in the ANZ public sector team. I'm based in Wellington, and today I'm going to be talking to you about best practices and patterns for building data lakes. Now the technique I'm going to be using to do that is to actually use an actual case study, a simulated case study drawn from the healthcare industry. Now, the reason I've chosen the healthcare industry is, one, it's an area that I've been focusing on over the last couple of years in New Zealand as a field solution architect. So I've had a lot of hands-on experience in that domain, but also because I think it's an area that pretty much everyone in this room has had encounters with, has touched your lives in some way. So I think the examples will probably be very familiar to you. Now, this is what we're going to build. This is the sample data lake, and it's a clinical data lake that's going to be working with hospital data. Now, I'm not going to bore you with a tedious walkthrough of this diagram, because you've probably all been through that and you'll know it's like pulling teeth. What I'm going to do instead is start at the beginning and start with some requirements, which is always a good place to start. So, generally, our best practice is to start small. Start with a small number of objectives, a small number of insights, a small number of data sources. And 3 seems to be about the right number. Now, the insights we're going to work with, I'm going to use 2 examples in the category of anomaly detection. And the anomalies we're going to be looking for are anomalies in admissions to hospital and discharges from hospital. We're also going to be looking for insights into the optimisation of maintenance schedules around some of the plant and equipment associated with the hospital. And we'll be touching real-time systems for that. And the data sources we'll be working with are the hospital's patient admission system, its discharge system, and all the collection of real-time therapeutic and imaging systems associated with running the hospital as well. So we'll get a good coverage of the different data types, different sort of data update frequencies and durability requirements. So we're going to start with the hospital discharge system. Now, the hospital discharge system pumps out a set of data called HL7. Now, HL7, if you're not familiar with the healthcare sector, is a fairly well-established format for encoding medical information, clinical information, and interoperating with other hospitals and health agencies. So the system's already producing this HL7 format, and what we're going to do is pump that data into S3 using the data sync service. And the data sync service is a little bit like an rsync service. It's constantly monitoring the arrival of new data and then pushing it to S3. Now, once it lands on S3, what we're going to do is actually look up the arriving objects based on their name in a list of predefined data sources. And this list of data sources is going to have things like metadata associated with those objects. It's going to have things like validation rules and partitioning rules. So we're going to pull that information from our list of known data sources and use that information to actually obtain the metadata and validate the schema. So we're going to check this is actually well-formed HL7 data. If it is, we're going to move it into the staging bucket, and we're also going to move the object metadata into a DynamoDB table. And that's going to be time-stamped. And the reason we do that is we're going to feed that object metadata into an Elasticsearch cluster. And this is going to give us the mechanism by which we can do data lineage analysis. We can actually look at the arrival of data as a time series, look at the metadata and do searches on that metadata using something like Kibana. We can also build data flow dashboards and that sort of thing once it's in Elasticsearch. So that's going to be a really powerful mechanism to build our metadata analysis capabilities in our data lake. So we've got validated data with metadata sitting in our staging bucket. The next thing we're going to do is we're going to try and discover the schema, and we're going to use the AWS glue service to do that, and in particular the crawler mechanism. And the crawler mechanism on a regular schedule will go and look at this staging bucket, discover the schema in that data, in that HL7 data, and publish that schema into a glue data catalogue, which is it's a Hive-compatible metastore, which means it's accessible to a whole ecosystem of MapReduce type tools like Spark and Flink and those sorts of things. So, and that glue data catalogue, as you'll see in the talk, is going to be the hub by which we're going to do all of our MapReduce analysis, our relational queries. So it really becomes the central focus. So that's one data source. Let's add in another one. Make a bit of room. So now we're going to hook into the hospital's managed admission system. Now, for the sake of the example, we'll say that this isn't actually an on-premises system. We'll say it's actually a cloud-based system. And oftentimes there's some really well-established players in this ISV managed hospital systems market. So we'll assume it's a managed service. It could be running on AWS, probably is, may not be though. And what this system is doing is pumping out admissions data in another medical format called FHIR. Now, FHIR is a REST-based protocol, and it pushes JSON transactions to a configured endpoint. And this is a very common pattern when integrating with clinical systems. And what we're going to do is use the Amazon API gateway to receive these admission transactions, these admission messages as they arrive. And the Amazon API gateway is going to perform the capture function. There's a set of Lambda code that will parse those messages, publish it to DynamoDB. But more importantly, for our data lake purposes, we're going to feed those JSON transactions into our raw data bucket. It's the same sort of bucket as we were talking earlier with our discharge system. And we'll go through that same process of looking up the catalogue, the data sources, validating the information if necessary, extracting metadata, feeding it into the Elasticsearch cluster so that we can do searches on it later on, and then moving into the staging area. And again, we'll use the glue crawler and the data catalogue. So now we've got two data sources sitting in our data catalogue. By the way, there's this particular pattern. There's a published solution blueprint that AWS has published that I'll show there'll be a link at the end of the presentation for this. Also, the Lambda code that I'm showing here that performs this validation and looks up the schema, extracts metadata is also available on GitHub as well. And I'll prepare a link for that. There's a link for that at the back of the slide as well, back of the presentation as well. So don't think you have to write all this code if you're trying to build a data lake. So we'll add a third data source. And this is the whole collection of real-time systems. Now, they're going to be probably quite a mixed variety of systems. They might range from imaging systems, sensors, it could be scanners, it could even be things like environmental controls. And what we're going to do is capture logging information from those systems and feed them into our data lake. Now, by their nature, this is likely to be a real-time type of system. So it's feeding in real-time information, and we'll integrate with the logging systems. The systems are probably built using tools like Kafka, Log4j, Flume, FluentD, a whole lot of open source and commercial products. And we're going to feed that CSV data into Kinesis data streams. And that's a sharded model that's able to sustain very large volumes of data. Now, Kinesis data streams is then going to feed into a Kinesis data firehose, which will batch up those tiny transactions into groups, publish them as objects into S3, and then kicks off the standard process we've been looking at earlier, where we're dropping that real-time data into a raw bucket. It triggers the process of looking up our data catalog, extracting metadata, and then feeding the data into the staging bucket, and then again running it through the glue crawler and making it available through the data catalog. Just as a special point here, with real-time systems, there's obviously a certain amount of latency with this sort of batched discovery and analysis process. And in some applications, you want to get a real-time window into what's going on in your real-time systems. So there's another related Amazon Kinesis service called Data Analytics that will actually work with a rolling window of time where you can actually run SQL queries against that data as it's flowing through the pipe in real time. So we've done our staging now. We've got a nice, clean, validated data lake to start working with. We've got a populated data catalog that's been populated automatically through our crawlers. Now it's time to do some analysis. And generally, a good place to start with the analysis is good old SQL, reporting and visualization. And the way we're going to do that is we're going to use a service called Amazon Athena. And Athena will hook into the data catalog, which becomes its data dictionary, and use the schema information and the location information in that data catalog to run SQL queries directly against the S3 data. So it basically makes the S3 data lake and the associated catalog look like an SQL data engine. And to the outside world, Athena is publishing supports protocols like JDBC, ODBC. So from a tool, from a point of view of a tool like Tableau or ClickSense or Power BI, QuickSight. It just looks like a regular old relational database engine like Oracle or SQL Server. So it means we can leverage our the existing business reporting tools and existing skills in those business reporting tools, but actually run the whole data lake off a non-relational engine. Now that'll take us so far, but bear in mind that we're actually querying very small SQL, very small objects in our data lake, and at some point the data lake is going to grow to a point where that's not going to be sustainable, at least for some types of queries, and we're going to have to optimize the performance. And the best way to do that is to use Amazon Glue, another aspect of Amazon Glue, to do compression and partitioning of that data. And the particular compression format this example is using is Apache Parquet. Now, Apache Parquet is a columnar compression format. It dramatically accelerates the performance of queries by up to an order of magnitude compared to querying the objects directly. Because Athena is a pay-per-query sort of service or pay-per-data scan sort of service, that also correspondingly drops down the cost of running the query as well. So it's basically a win-win situation if you can use compression in addition to that. You can also use partitioning, and partitioning is a really powerful technique when there's a match between the common constraints that you're including in your SQL queries and the partitioning key that you're storing the data under. And if you're thinking of an example, if you imagine you're using year and month as a partitioning key, then the query that says, show me all of the patient discharges for the current month is going to run extremely quickly, because Athena can look at that partition information and say, I only need to hit a subset of my data when I'm running the query. You can also use that glue process to do standardization of things like date timestamps to make the life easier of the people writing the SQL queries. Now, for some parts of your data, even Athena with the Parquet compression is not going to be good enough. And some set of users, maybe the people doing, in this case, doing follow-ups and referrals to GPs, might say, well, we really want to have, there's a really tight set of data that we need to access very quickly related to recent discharges from the hospital. So it'd be really good if you could speed them up for us. So what we're going to do is drop in Amazon Redshift onto our data lake. And with Redshift, we can load subsets of data from S3 into Redshift, but also with the Spectrum feature, it doesn't become a binary decision that the data is either in Redshift or it's not. We can use the Spectrum feature to perform unions and joins with data that's still sitting in S3. So we don't have to load the entire data set into Redshift. We can just load a hot subset of that data into Redshift and have the best of both worlds. So it's a really good way of balancing the cost performance of your data lake. Or your relational queries. And obviously Redshift still supports those standard JDBC, ODBC protocols. We can continue using familiar tools. Now, that's all well and good for the business reporting guys, but what about the data scientists? They're not going to be really happy if you just give them a bunch of SQL tools to work with. They're going to want to operate in, say, a managed notebook environment like Zeppelin or Jupyter Notebooks. They're going to want to be able to run Spark jobs against their query. So we can help them out by using the managed notebook features of Amazon EMR. And another aspect of the Amazon EMR that's really powerful for using with data lakes is a thing called the EMR file system, or EMR-FS. And that acts as an overlay that makes an S3 set of buckets look like a Hadoop file system from the perspective of tools like Spark. So you don't need to shuffle data from S3 buckets into HDFS file systems and back and forth again. You can directly query the data in place using EMR-FS. So that's taken us so far, but what about machine learning applications? What about machine learning? So we've basically just scratched the surface here. So with our medical services, we can run a service called Amazon Comprehend Medical. And Comprehend Medical is able to take some of the clinical notes written in free format text within our HL7 messages and extract the clinical terminology from that text. So it's able to pull out things like diagnoses, medical conditions, medical prescriptions, anatomical terms, symptoms, all that sort of thing, and then represent them as JSON structures. And you can see an example here where we've got a piece of unstructured clinical text. We've run it through Comprehend. There's the JSON representation of the highlighted terms that Comprehend's produced. And on the right-hand side at the bottom, there's a diagrammatic representation that Comprehend produces to help you actually validate what's actually coming out of Comprehend. Now, this allows us to do a little bit better than just working with keyword matches on the text, because as you probably guess, if you're just matching on words like rash, for example, and the clinical notes say no sign of a rash, then your keyword search is going to say, oh, there's a rash here, but you know there's a negation term in there. Now, Comprehend because it does natural language processing, can recognise those negation terms. It can recognise quantifiers, and so you're working on a firm basis when you're running your data lake. So we're going to plug Comprehend into our data lake. It's going to it's going to be triggered by the arrival of unstructured data in our staging bucket, and we're going to use a Lambda function to call Comprehend, produce those JSON structures. We're also going to go a step further and actually do matches into clinical terminology or taxonomy databases like SNOMED and ICD-10, which are taxonomies for classifying diseases and symptoms and diagnoses. And then we're going to store that codified data in the directory called medcoded. So now we're getting a little bit further down the track with the medical domain with our data lake. Now, Comprehend is really good if you're working, that's a pre-packaged application service, pre-built on the corpus of medical knowledge. But we want to actually go a little bit better than that. We want to actually look for anomalies in discharges and admissions to our hospital. So these are things like, say, an anomaly might be an immediate readmission of a patient for a related condition soon after a discharge. We're looking for things like that. Now, there's no Amazon pre-built service that's going to do that for us. We're going to have to train our own system to do that. And we're going to use SageMaker to do that. And SageMaker's got a couple of dimensions to it. It provides a notebook type of environment for data scientists to be able to leverage tools like Redshift, Amazon Athena, run sort of experiments and queries. They can build training models and experiment and iterate with those training models in a very friendly, interactive environment. And at some point, and this is generally referred to as a feature engineering process, and at some point the data scientists will say, well, we think we've actually got a working model for detecting anomalies in our discharges and admissions, and we want to publish that as a model. So the next thing they will do is use SageMaker to publish the model inference endpoint, and then our data lake is able to leverage that by writing a Lambda function triggered on the arrival of our medically coded data to go out to present the admission or the discharge transaction to the model inference endpoint, and the model inference will then score that transaction to say what's the probability this is an anomalous discharge or a readmission. And that scoring result can be fed back into the data lake. Now, once we get a little bit more elaborate, we can actually build an entire workflow around this inference chain, and we can use step functions as a way of doing that. So you can have a whole series of inferences and models being evaluated as part of our data lake. So we're sort of closing the loop now, and you can see this is basically where we started. What can we learn from this? So some pro tips, I think, from this exercise. First of all, set some achievable objectives for your data lake. A small number of business insights, a small number of data sources, 3 sprints, that sort of thing. Really good place to start. Build a data catalogue that you can use to trace object lineage or data lineage and query it, and also to discover schemas automatically so people aren't running around making sure the data is what they think it is. Use Parquet transforms to actually optimize your queries, to use columnar compression and speed up your queries. You can process the S3 data directly using on EMR clusters using EMRFS. So don't move data to and from S3 and Hadoop file systems. Process it in place using EMRFS. Use machine learning application services where they're good enough to do the job, but then extend that further by using your own machine learning models to enrich the data lake and feed back into the data lake. So build a virtuous cycle that way. So I've presented a story here based on a medical case study, but I want to introduce David Scott from the Network and Asset Intelligence Unit at the Transport for New South Wales. And David's going to present a business perspective on the value of a data lake. and also presented quite a different domain, which is based on their journey planner application. So this is basically journeys as opposed to medical information. But what you'll find, I hope, is that when you look at some of the David's architecture and some of the outcomes, you'll see those same best practices and patterns being applied in a very different domain. And I hope they'll convince you that this is actually a generally applicable set of guidance. So I'll hand over to David.
Thanks, Craig. Good morning. Okay, so my section of the presentation is going to be quite different to Craig's. I'm going to probably focus almost entirely on the journey we've been on in terms of developing really a capability which is designed to deliver a step change improvement in customer experience for the citizens of New South Wales, or anyone who really comes to our state and uses our transport options. So like I said, our function is really established to come up with ways that we can help improve customer experience. The domain that we've focused on for the last couple of years has been specific or exclusively roads. So if I go back, when I started with Roads and Maritime, which is within Transport for New South Wales, it was a very, very siloed data environment with a really low level of data literacy. The ability to access information, to make network improvements, or to influence customer choice was really difficult. Yeah, and so we've really focused over the last 2 years in building capability across all these different domains, whether it be visualization, data science, forecasting, or even partnering with third parties to buy data that can help us just make better choices about how we improve our roads network. And I think underpinning all of this was an ethos that we established within the group, which was about democratizing data internally to really empower our colleagues to make better choices. Okay, so my background being banking and telco, in those industries, access to information is an expectation. Okay, but coming in the public service, what I found is people use that information as power. Okay, and so there's a vested interest to lock it away and use it as the one thing that you know that everyone else doesn't know. Okay, that doesn't work for us, and it definitely doesn't work for our end customer. So I just want to give you a bit of insight into the journey that we've been on. I'm hoping there's a few people here who are in the public sector. I think this is actually a really exciting story for us, and I'd hope that you have the opportunity to do something yourselves, which is quite similar. So if we go back, rewind to February 2018, we had about 5 people with the skills and the ability to access data, to understand what was happening on the roads network. And maybe 2 or 3 of our stakeholders, we might just let them access the information, but they had to pass a series of tests before we'd enable them. Fast forward to when this slide was done in July, we'd increased our numbers to about 60 analysts, data scientists, engineers, both a combination of permanent headcount and plus augmenting with various partners. And we've also started enabling our internal stakeholders. So in addition to my group having access to a whole new range of information on a single platform, which is AWS, we've now enabled people across the organisation to have access to better information, which is really starting to ramp up in terms of the value that we can deliver to our end consumers. From an operating model perspective, I've heard a couple of people speak over the last couple of days. We are fully agile, so we run scrums. It's a DevOps environment, so we've got the people who are in development on AWS very close to the people who are working with stakeholders, understanding the opportunities and the problems for the business, and really focusing on delivering value. So where I started, our vision is to deliver a step change improvement in customer experience. And so what that means when you talk about agile ways of working, every single thing we do needs to tie back to a customer outcome. And Agile's been really important in making sure that we keep our team really aligned and focused on high value initiatives. And then from a technology perspective, if I go back to February 2018, we weren't using the right tools. our version of an enterprise data warehouse was a SQL server, which was completely not fit for purpose. We've now gone to a full AWS stack. Wherever possible, we've stayed really close to the native technologies. And that's allowed us to really ramp up quite quickly. So getting access to AWS for my group really only started to ramp up in February this year. And we've already got over about 130 terabytes of data. And I've got one example that I'll talk to in a second where we're really starting to deliver high-value initiatives, but the focus isn't just on doing management reporting or supporting our more traditional infrastructure build. The way we're moving is towards using technologies like AWS that allows us to not only build the data lake, structure the data, but also build applications that are customer-facing. So instead of being limited, like many of the other groups that I've worked in the past, where your main focus as an analytics expert is on improving business processes or driving more sales. Really what's happening here is our people are focused on delivering better outcomes for customers and really being able to take products all the way through to market. So as Craig mentioned, this is actually a new product that we've launched only in the last few days. We're calling it our Journey Planner. So I might take you back, I guess. Like I said, we really spent the last sort of 18 months building capability. But what I wanted to do with my group was give them a bit of permission to challenge the status quo. So the first place we started was we said, okay, we've been doing a lot of dashboarding, a lot of analysis to really understand what's happening in terms of demand. Let's start communicating out to the end consumer. So in December, we released some forecasts, where we communicated with the end customer and we said, okay, these are the places around the roads network where we expect you're going to have a pretty bad experience leaving Sydney around Christmas. So we did that. We got a little bit of traction. I wouldn't say it was too much. But I guess we wanted to keep going. And so we in April, released some more information for Easter. Again, really not really giving the end consumer any tool, but just giving advice. Okay. In June, we wanted to ramp it up a bit. So we laid down a challenge for the team. We gave them 6 days. And we said, okay, in the next 6 days, we want you to come up with an application that we can release to the end consumer to help them plan their journeys around the June long weekend. So we came up with our version 1 of the Journey Planner. It did not look like this, okay, but 6 days, expectations can't be too high. Anyway, it was an amazing result. So of a zero base, we had about 13,000 hits to our microsite. We were able to identify really significant changes in demand for some of those hotspots. So for anyone who knows Sydney, think about the M1 at Wahroonga, leaving Sydney going north, or the Hume going south. We could absolutely measure some real changes in demand and seeing people change their journeys and move their journey times to a time when the amount of traffic was going to be a little bit lower. So with this new version now, we've now modeled 16 different road segments across the network where we know that we've got some pretty significant congestion. The idea is it's always on, so you can forecast out for about 7 days, and you get a pretty good expectation as to what we expect. We've used just basic linear regression to do the predictions. We get an R-squared for the techs in the room of about 0.97, so it's very, very accurate. We can explain almost all of the variability in the demand with a really simple model. And what we've also done is we've given people the ability to go back in time and evaluate what the demand was versus our forecast. Okay, and so this is live now. Feel free to jump on, except wait till I'm finished talking. And so if you look at a corridor like Parramatta Road, where we've just opened the extension to the M4, our models are wrong. Okay, and it's because with this approach, you need a bit of history. But what it shows is, and what the big benefit to us as the roads agency, is we can now start to explain the benefits that we can deliver to the end consumer by opening these new corridors. So we're seeing about 200 cars per every 15 minutes decrease on the Parramatta Road, which is leading to much more much more consistent journey times. Anyway, so yeah, I think for us, this is very much a work in progress. It's all using AWS technologies. Our vision is to make it real time, so the demand data that you see there, which we pick up from our traffic light system, we're updating daily, but in the next couple of months we do intend to introduce real-time data to this application. And so the intention is, or our vision is that over time people will change decisions about when they travel and start travelling at times when they're going to get a much better experience. So I'm not going to go through the technical services. I think Craig would do a much better job than me, but I think if you do have any questions about these services that we have applied, feel free to grab me after. And that's it. Thank you.
Thank you, David.
Thank you, Barry.
It's the promised links to any of those clinical information sources or the data lake pattern if you need them. Thank you.